All right, round two. So now we're getting into some of the first laws, some of the easier laws that pertain to gases. All right, so the first one is called Dalton's Law of Partial Pressures. All right, pretty straightforward. Basically, what it says is the total pressure of a mixture of gases is the sum of its parts, right? Which makes sense. And the reason we need to think about that is gases can expand. They take up their entire container. And there's also always more than usually one gas in there, right? Take our air for example, right? And so the simple equation is this. The total pressure is equal to P1, P2, P3. And what the P1, P2, P3 is the pressure of gas 1, gas 2, and gas 3. And those would have to be different gases. So it might be CO2, H2O, and H2, right? And so we're going to do, I'm not going to do any examples mathematically on this video, but I'll have some separate videos of individual math. But that one's pretty straightforward, right? If we know our pressure total, we can subtract to find one if one of these is missing, or if we have a bunch of the sub parts, we can add up to a total if we need to. All right, so taking a look at this, right, this is basically what our air is. So PT would be our air on the right hand side, and the sum total of air, and you can see down here it's 100.3 kilopascals, is the combination of our oxygen and our nitrogen and argon and water and CO2, right? And we can see from before, right, based on pressure, but this is also kind of really just based on percentages, is we have 70.1 kilopascals, or basically 78.1% of our air is nitrogen, oxygen being vastly the next best thing, but then we can see there's CO2, H2O, and actually quite a bit of argon in there. So that's a realistic view of how partial pressures can affect us. Another one, very specifically, is for divers, right? In that tank, it's not just pure oxygen, right? There's a combination of nitrogen and oxygen depending on the depth to which you are going to be diving. So that combination is going to affect your breathing in there. So in that tank, it's not just oxygen. Obviously, there's some other particles mixed in. So we'd want to know that, and the total pressure of that would be the air pressure in there. All right, so that's pretty straightforward. Next one is Boyles Law. Okay, so Boyles Law, for these next three, we're going to keep a couple things constant, because anytime we're trying to research something, if you have more than one moving variable, right, it's not going to work very good. So those four variables that we took a look at, we're always going to keep two constant and change one and see what happens to the other. So what we're keeping right here is the gas molecules, so really the moles, and we're going to keep the temperature constant. So temperature has got to stay the same. The number of moles of gas cannot change. So think about a balloon in a room. Room's not going to change temperature. If you tie off that balloon, the molecules aren't going to change. So what we're going to be looking at is the difference between volume and pressure. Okay, the difference between volume and pressure. If you really go back and you think and you rewatch the video of the pop can experiment, that's what was going on there a little bit. So we have the equation here, again, pretty simple. P1 is the pressure initially, and V1 is the volume initially. And then what we do is we change one of those and we come up with a new pressure and a new volume. You know, so if we have, you know, a pressure of 1 atm and a volume of 100 liters, right, and we have a new volume of 200 liters, what happens to our pressure, right? We're going to be able to make some of those easy calculations. But that's Boyles Law, right? All right, some real life applications, right? If we take a balloon and we squeeze it, right, we're increasing pressure, and what's happening with the volume? Okay, think about that one. Another one that we can look at is an aerosol can, right? We open it up and you can see in this case, we release some of that pressure. What is happening to the ability of those gas molecules as they enter this air, as they enter this new system that's not as constricted, right? What's going on there? Well, this is a pretty good animation of what's going on. So you have your pressure down here, and we have our, as we are increasing pressure, temperature is holding constant. right, the number of molecules is holding constant. So as pressure goes up, volume is going down, right, as we change the system. And so that's a good quick look at how that kind of works out. So the next one is Charles Law. Okay, so Charles Law, again, same thing. We're going to keep, in this case, gas molecules again. So we're going to have a balloon, then we're going to tie it off. But the pressure is going to also remain constant, right? So that means volume and temperature are going to change. Okay, and so this equation is slightly different. If we take V1 divided by T1, that's going to equal V2 divided by T2. Okay, so as volume changes, how's that going to affect temperature, or vice versa? So the one thing I want to say is, if you are ever trying to solve for a temperature, just take the inverse of this equation. So you can also say, because it's the same ratio, you can also say T1 divided by V1 is equal to T2 divided by V2. Okay, what some people do is they leave it this way, and then they think they're solving for a T, and really it's going to be the inverse of T, and then your answer is not going to work out well. So make sure you do that. But there's also one more thing we got to take a look at. I said we're going to come to this, right? Is we cannot use degrees Fahrenheit, and we can also not use degrees. We cannot use degrees Celsius. So we always have to convert, right? We can't end up with zeros. It would be weird if all of a sudden we ended up with zero volume, like it just magically vanished. And in order to make sure that doesn't happen, as long as we have Kelvin, in typical situations, we're going to be good. It'd also be weird to end up with a negative volume, like where did it go? And if you had negative temperatures, we would have the ability to do that. So the important part is when we take a temperature, generally it would be in degrees Celsius, we want to add 273 to that to get our Kelvin. Not hard, you just got to remember to do it. All right, so here's a scenario where Charles' Law is being used is in an air balloon, right? So we're heating up the air, and what does that heating up of the air do? It's expanding the volume of the balloon as it gets warmer and warmer and warmer. And so it creates less and less density compared to its surroundings on the outside, and then it's able to go up. Another really useful or practical use of the Charles Law is a basketball, right? So a basketball, if the temperature drops, the volume of the basketball is going to do the same. So if you leave a basketball outside and it's cold outside, you're going to come back to it, and maybe it's a bad basketball and the air has changed, but generally it's because that volume has just gone down a little bit because those particles aren't bouncing around all over, right? It takes those air molecules to bounce around to keep pressure on the outside of that ball. If they lose energy, right, that ball's going to shrink a little bit just because of the balls inside. All right, so here's another look at it. If we're holding pressure constant and we're holding gas molecules constant, right, here's the basic look that we get, right? As temperature goes up, volume goes up. As temperature goes down, volume goes down, right? Just a nice quick look at that. Next one is our Gay-Lussac law, right? And so this guy, same thing. We're going to hold two things constant. In this case, we're also holding gas molecules. We're holding the moles of gas constant, right? Nothing's going in, nothing's coming out. And then we're going to hold the volume constant. So we're not going to change the size of our container. So what we are changing is temperature and pressure. And so this looks very similar to the last equation we just got done taking a look at. So we have pressure 1 divided by temperature 1. Again, we can invert that. And pressure 2 divided by temperature 2. Again, here we also, because we're dealing with temperature, it's got to go back to Kelvin, right? So make sure you do that. But the same general thing, as temperature increases, pressure is also going to increase if that volume doesn't change. Right? So if we're keeping this cylinder, if we're keeping this core the same, as temperature goes up and those molecules start bouncing around, right, that pressure is going to increase, which is where some bombs come from, right? That's the main idea. Pressure cooker, right? Pressure cookers are used to make food quickly because not only does it get warm, but it also keeps the pressure in, which means we get kind of the dynamic duo of things being able to cook a little bit faster. They're also used to make bombs once in a while because of that effect, because they're able to hold in that steam or those gases so well. And then all of a sudden, it has to go, and it will go because gases are very powerful. Another one is a bullet, right? It's coming out of that chamber because as it heats up, those gases are expanding, and then boom, out that barrel comes the bullet, and that's where the recoil comes in, and you can see some of those gas particles. It's got to go somewhere, so we're releasing in a particular direction, but we get the Gay-Lussac law to help us with that changing temperature pressure, right? So the animation would be the same. So here's a graph, as one goes up, the other goes up. Pretty easy to see. And so the last one we're going to talk about right now is the combined gas law, which, like it sounds, is really just taking all three of those laws and putting them together, right? The only thing that we're holding constant in this one, again, is the number of moles, so we're not even going to see that. But in the end, what we get is this: P1V1 divided by T1 is equal to P2V2 divided by T2. So in the end, really this is the only one we need. The other three, given the right situation, makes it a little bit easier to think about and a little bit easier to do. And I'll show you that when I show some practice problems. But if out of this, if you just use this, right, even if one of them's being held constant, right, you can still put, if it said volume is going to remain at 2 liters, if you put 2 liters there and 2 liters there, they're going to cancel each other out. So you can use it, or if it doesn't come up, you can make up a number. But this out of the 4, well, this is going to be the 5th, but out of the 3 main laws that we just got done talking about, if you are just able to use this one effectively, you're going to be pretty good at what we need to do. All right. See you in the next video.